So, welcome to the third of our series of lectures on solid-state chemistry. We just noted that the best packing for spheres is either cubic closest packing, which forms a face-centered cube, or hexagonal closest packing. The hexagonal closest packing provides an interesting case, but the math tends to be sort of complicated. It's simpler to look at the cubic packing and its variations, and so that's what we're going to do to start with. We're going to look at cubes. We have three possibilities for simple packing. We have the simple cube, we have the body-centered cube, where each of the ones at the corner, and there is one in the center of this cubic structure, and finally we have the face-centered cube, where on each of the square faces there is one directly in the center, but nothing in the actual center of the structure. We can look at the volumes of the various cubes in terms of the simple spheres that are forming the corners. For the simple cube, the edges are each 2r, so the volume of the cube is simply 8r cubed. For the body-centered cube, it is the long diagonal of the cube that is 4r. The two corners touch the one in the center. And in this case, the edge ends up being 4 divided by the square root of 3r. And so the volume is simply 4r divided by the square root of 3 cubed. For the face-centered cube, it is the diagonal of the face that is 4r. This makes each of the edges 2 square root of 2r, and the volume of the whole cube, therefore, 2 square root of 2r cubed. We can use this sort of information in various ways. For example, if nickel, which has a density of 8.9 grams per cubic centimeter and happens to form a cubic closest packed structure, what would that make the radius of a nickel atom? Well, we'd simply have to figure out what size atom in a close packed structure would give the right density for nickel. So we got to start out with some bit of information about nickel we already know. Well, the atomic mass of nickel is 58.69 grams per mole. The density, 8.9 grams per cubic centimeter, would give us the volume of a mole of nickel. A mole is 6.022 times 10 to the 23rd atoms of nickel, and there are 4 atoms per unit cell in a face-centered cube. So that gives us the volume of the unit cell. 4.38 times 10 to the minus 23 cubic centimeters per cell. Well, the edge would therefore be the cube root of 4.38 times 10 to the minus 23rd cubic centimeters. And we said the edge of a face-centered cube is 2 square root of 2r, and this would give us an r value for the nickel atom of 1.246 times 10 to the minus 8th centimeters. And so we can get a size for the atoms. We can also solve the problem looking at it from the other way around. Suppose for some reason we were aware that barium has a radius of 2.18 times 10 to the minus 8th centimeters, and it forms a body-centered cube. What would that make the density of barium? Well, again, 1 mole of barium, 137.33 grams. 1 mole is 6.022 times 10 to the 23rd atoms. There are 2 atoms in a unit cell. And given that it's got a size of 2.18 times 10 to the minus 8, then its volume for the unit cell would be 4 times 2.18 times 10 to the minus 8 divided by the square root of 3 cubed, or 1.276 times 10 to the minus 23rd cubic centimeters, which gives us a density of 3.57 grams per cubic centimeter. And so we see the pure elements, the metals, tend to either form a cubic closest packed or hexagonal closest packed array, with some of them also having the body-centered cubic structure. And that's true for almost all the metals. The exceptions we run into on the periodic table tend to be the nonmetals. And of course the nonmetals we can't model as simple spheres because many of the nonmetals in fact form molecules, like the halogens and phosphorus and sulfur and oxygen and nitrogen, and so their crystal structure isn't going to be that of a simple set of spheres bonding together. But for the metals, overwhelmingly, they do fit into our simple pattern, and so we can use the density of the solids and what we can tell from crystal structures to deduce the approximate size of the atoms. And that brings us to the end of our lecture on solid state for the elements.